Hey everyone, I'm Aditya Bhattacharya, currently working as a data and cloud platform engineer in West Pharmaceuticals, and I'm a AI researcher in Must AI Research Group. So today I'm going to present you a session on computer vision using deep learning. So first I'll start about myself a little bit. So about me, as I said, currently I have been working in West Pharmaceuticals in Bangalore as a data and cloud platform engineer. And previously I have worked in Microsoft as a cloud infrastructure developer in the secure infrastructure domain. And I have worked as a research intern in Intel in Smart Homes and Buildings Group in I2R. And apart from that, I have graduated from VIT University. And as I had mentioned, I'm a part of Must AI Research Group and working on a lot of AI research projects related to various domains. So the picture of me over here, if you see, this is one of my initial works as of Must AI Research Group. So this is a pencil sketch image that I generated from an original image. And yeah, I'm working on a lot of computer vision related projects. So, coming to my interest, I'm really interested to know and work around the unstructured data domain, which includes vision, text analytics, as well as speech processing. So, my current focus is on problems related to the vision domain. Now, moving on. So, these are the broad topics that I want to discuss in today's session. I'll start with convolutional neural networks because for computer vision, CNNs are extremely important. So all of you should know the basic concepts of CNN so that we can progress further. Apart from that, I'll start talking about certain popular coordinate architectures so that while implementing your solutions, you can start with these architectures and maybe based on the performance, you can select your architecture or even tweak your architecture a little bit to modify it and make your own architecture. So moving on, I'll be talking about few popular concepts related to computer vision like data augmentation, transfer learning, and then I'll be moving to the problem domain of object detection. After that, I want to talk about neural style transfer and then move on to the latest image generation algorithms on which people are working on, like generative adversarial networks (GANs) or and variational autoencoders, or popularly known as VAs. So these are the broad topics that I am planning to discuss today. Now, according to me, typical computer vision problems or solution domains can be categorized broadly into these four categories. So it can be related to image classification, it can be related to object detection, it can be related to neural style transfer, and lastly, it can be related to image generation. So classification is all about how do you classify a particular picture is having that particular object which you want to find out in that image or not. For example, if you have an image of a cat inside, or let's say from this particular image, you are supposed to say whether this image belongs to the category of cat or not. Now, in object detection, so object detection is basically about two things. It is about classification as well as localization. So in object detection, not only you classify whether that particular object exists in your image or not, but you try to find out the exact location or the boundary boxes like in within which your object exists. So this is about object detection. Now in neural style transfer, you would have a base content image, then you will have a style image, and the output image which you want to generate should have the contents of your content image but generated in the form of your style image. So this is about neural style transfer. This is very interesting. I'm going to show you a few demos if possible. Then moving on, we have the image generation category in which you use popular algorithms like GANs or VAs to generate specific images from like existing images. For example, if you have a let's say bunch of human faces and using those algorithms, if you want to train and generate your own human face images, so this is how it is done. So it is still not perfect according to me. Like there are a lot of works that are happening, but overall it will give you outline structure which is similar to human faces as of now. But yes, a lot of research works are going on in this domain and we are significantly improving. Now moving on to convolutional neural network, our first topic that I wanted to discuss. Now first, let me ask you, why do we need to go for neural networks or convolutional neural networks? Why not classical machine learning approach? Well, when I started working, I started with classical machine learning approach, and I observed that in classical machine learning approach, you need a lot of research related to the particular features that you want to extract from your data set, especially in images, and it's really difficult in doing feature engineering, particularly to unstructured data. So it is yes, it is time consuming, and you need specific domain related knowledge for such classical machine learning approach. And even if you are able to come up with the best features or the best feature sets, still I have observed that the accuracy of the algorithms or the final output models which you develop are very less as compared to what we get for CNNs. So in CNN, the accuracy of the algorithms were really good, and it's much more reliable and easier to train and implement. So I won't go much into the details of how your neural network architecture looks like, but this is generally how a typical neural network look like. You will have an input layer, and you will have a hidden layer, and you will have an output layer, and these are all individual uh, neuron units. So it's a fully connected network over here, as you see. And this is how a typical CNN architecture looks like. You will have an image. You will try to translate your image into a matrix. From there, you'll try to do a convolutional operation. I'll come to it, what convolutional operation does. Then you try to apply the concepts of pooling. Then you try to, you get a flattened image like this, and then you try to pass it through fully connected network. And finally, you try to pass it through an activation function. So that depends upon your like problem which you want to solve. But this is how a typical CNN architecture looks like. So how does convolution actually work? So as I said, you first convert your image into a matrix format. So for colored images, you will have 3 channels for RGB, but in this typical case, what we have taken, it's just a 6 by 6 matrix. So we can consider this as a 6 by 6 cross 1 for 1 channel. So you might consider that your image is a grayscale image which has only 1 channel. So once you convert your image into a matrix format, then you try to do the convolutional operation using a filter over here. So what it does is you try to basically overlap your filter over here and try to do an element wise multiplication, and you try to take the combined sum of it. So for example, in this case, it will be 3 into 1 plus 1 into 1 plus 2 into 1 plus 1 into 0, 0 into 0, 3 into 0 plus 1 into minus 1, 7 into minus 1, and plus 5 into minus 1. So the output which you get is minus 7. So likewise, you try to move your filter from this particular region to the different region, and the amount by which you move can also vary. So I'll come to those concepts, but let me talk about something related to the dimension of the output matrix what you get. So if you have an n cross n image, and if you have a f cross f filter, this is the final dimension which you are supposed to get, n minus f plus 1 cross n minus f plus 1. So for a 6 by 6 image and a 3 by 3 filter, your output should look like 4 by 4. So in such a case, this is called as valid convolution. Now why valid? I'll just come to it, but before that I want to talk about padding and stride rate convolution. So let's talk about stride first. So what is a stride? So as I said, the amount by which you shift your entire filter region can vary. So by default in this case it is 1. So in such a case your stride equal to 1. But instead of moving just 1 box towards your right, you might start from here, like move 2 box towards your right. You can start from 1, or even you can start from 2. In such a cases, your stride will be 2 and 3 respectively, like how you jump your the stride length, what you call. Now there can be certain requirements where you can tell me that, okay, I don't want an output matrix of dimension 4 by 4. I want my output matrix to have same dimension as my input image. How do we do that? So in such a case, we apply the concept of padding. What we do, we add few extra, let's say, matrix units over here, and we fill it with 0, and we call this extra regions what we are adding as pads or padding. So in such a case, if I want an output matrix of the same dimension 6 by 6, so I need to add few padding layers in this side as well as in this side, and similarly in the rows also. So in such a typical case, my padded image matrix will be of the dimension 8 by 8 in order to get an output of 6 by 6. So this is how the typical formula looks like. So if you have an n cross n matrix and f cross f filter, your output padded or the output matrix should be of this dimension, n plus 2p minus f divided by s plus 1 cross n plus 2p minus f divided by s plus 1. So here P stands for padding and S stands for the amount of stride which you are adding. So in such a case, it is called same convolution because you are keeping the same dimension of your output matrix as that of your input image matrix. Now in CNN, edge detection is very important. So typically your edge detection is done at the initial layers of your architecture. So what you do, you try to pass your input image through different filters. So in such a case, if you pass the main base image that might contain an entire human face through a set of vertical and horizontal filters, this is how your output will look like. So basically you are trying to detect the vertical edges and the horizontal edges. And in modern deep neural networks, the weights of these filters, as you see, you don't often fix it. You let your algorithm calculate the weights of your network. So it actually helps you to find out what are the exact features that have more importance for your problem which you want to solve. So those weights, it's automatically calculated by using the concept of back propagation, and then you do forward propagation to apply those weights. So I won't go into much details of how a deep neural network works. I'm going to talk mainly related to convolutional neural network. But these weights, as I said, you don't fix these weights. These weights can be calculated based on the algorithms which you use. Now let me talk about something related to pooling, because pooling is again a very interesting concept that is used. So in pooling, what you typically try to do, the filter that you add over here, so there can be, like, I have used mainly two types of pooling. It can be max pooling or it can be average pooling. So in max pooling, the same convolutional operation what you do, instead of adding or doing element wise multiplication and taking the total sum of it, you take the maximum of that entire filter region when you try to overlap, and then you try to form it in your output layer. So that is for max pooling. So in such a case, if your 2 cross 2 filter tries to move from here with a stride 2, and when it starts from here in this region, it will take the max value of 6. In the next region, it will take the max value of 8, and similarly it will take the max value of 3 and 4. So in case of average pooling, it will be the average of the entire box. So it will be 7 plus 8 plus 13, 13 by 4. So the answer over here will be 13 by 4, and likewise it will vary. Now, as I had initially mentioned, for convolutional on RGB images, for RGB images you will have three channels for red, green and blue. So when you try to use your convolutional filter over here, the filter will also have three channels. So the number of channels of your filter will be same as the number of channels of your input image. So the dimensions will accordingly vary, but your output dimension will still remain the same. Now let's say with the same input image you are trying to apply multiple filters. So let's say 3 filters if you want to apply. So in such a case, your output dimension will become 4 cross 4 cross 3. So the third dimension what you're getting depends on the number of filters that you're trying to apply. And sometimes this filters is also known as kernels. So in some places these are referred as kernels, so don't get confused with the term kernels and filters. Now, as I said, this is how a typical deep convolutional neural network looks like. So I'll move on to the next concepts. Yeah, as I said, I wanted to talk about certain popular CovNet architectures. So when I started with LENet. So in LENet, typically you have your input image, then you have a layer of convolutional operation, and then you try to pass through a max pooling, and then you do another layer of convolution and another layer of max pooling. After that, you will have a fully connected, you try to flatten your image and then try to pass it through a fully connected network, and you usually keep your activation as ReLU, or it can vary depending upon your type of need. And then you again pass that output through another layer of fully connected neural network, and finally you will have your output layer. So in such a case, the depth of your network will be 5, because convolution and max pooling are considered as uh, one set of operations. So it will have like one layer in together. So it will be 1, here 2, this will be your third layer, fourth layer, and finally you will have your output layer. So it will be having 5 layers. Now if you want to get a better accuracy, and if you can afford more computational cost, I would suggest to go for something like an AlexNet, which have more depth and more layers, and the accuracy which it gives is much better. And slowly you will have other popular architectures like VGG and InceptionNet and RestNet. So each layer or each architecture are much more complex than each on them, and it depends on how much computational power you can afford and what is the exact accuracy you need depending upon the criticality of your application. By the way, this InceptionNet, the name Inception actually came from the movie Inception, which shows one layer inside another layer, and so on it goes on. So it's a very interesting architecture, so you can try this. So I won't go much into the details of this architecture because I want to keep the overall target for this session very high level. In case if you have any further queries, maybe we can take it offline considering the time constraint which we have for this session. Moving on. Now I'll talk about something called data augmentation. Now typically, what is data augmentation? Now when I started working with computer vision problems, the size of the image set is a huge problem. Trust me, it's a huge problem. No matter how many images you have, it won't be sufficient for the solution which you want to come up with. So data augmentation is actually the process of using your same data set, and you try to do typical operations like this listed over here, and try to you get a much more bigger data set. So I'll again come to the details a little bit, but first, why do you need data augmentation? So as I said, the data set, the amount of data set what you have is never sufficient, and with smaller data set, overfitting is a huge problem. So overfitting in general is a very big problem for computer vision domain. So for fighting such overfitting problems, you need to have a much bigger data set. There are other techniques of adding regularization as well. I won't go into the details, but data augmentation typically helps you to expand your data set from available data in an unbiased way. Now, why unbiased way? I'll come to it. So let's say if you have the base image or the original image of a cat like this. Now from this, you want to expand your data set. Typically, what you try to do, you try to apply certain matrix or image related operations like mirroring. So you try to mirror the cat image, and you get another new like data image. So you're not adding bias for that particular cat figure. It's like looking at your cat from different angles, from different postures. So it helps your algorithm to improve the confidence as well, because you're giving like all sorts of overview for that particular object or the image. So these are the typical operations you try to apply for doing data augmentation. You try to apply the concept of mirroring. You try to do something like a random crop. You take a random crop of your particular cat. You try to do rotations. You try to do shearing. You try to do warping, and sometimes even you try to do color shifting. So what you do in color shifting is that you add certain weights for the RGB fields if you have. So for example, if the RGB value of this image is 50 50 50, you try to add a RGB value of, let's say, 2000. So it tries to shift your color domain of that particular image, and you get a different shade of that image. So you can consider that you got that particular image at a different environment light settings. Okay, so I'll now talk about something very important. It's called transfer learning. So in deep learning approaches, instead of training your network from scratch, because training your network from scratch can be very difficult, you need a very large data set, you need a very high computational power, and you need to spend a lot of time to complete the training and make it more accurate. So instead of training your like network from scratch, what you try to do, you try to use a pre-trained network or model and fine tune it or retrain it with the different labels of your application and try to come up with the solution. So one example, if you want to deep dive into it, is working with ImageNet. So I'll come to it, but I'll first talk about why do you need transfer learning. As I said, computer vision problems require a very large data set, and it can be very difficult to get the data set all the time. And CNN architectures or algorithms are not extremely fast every time, but with transfer learning, what you try to do, you try to use your algorithm on pre-trained network. So it makes your entire process or solution much faster, much reliable than training the entire data set from scratch. So in transfer learning, what you do, you use your pre-trained network with the new set of data. You try to add your required task, or basically you try to fine tune your network, and then you try to use an activation function which will be specific for the type of solution which you want to use. So for classification, in ImageNet, actually it has been trained over 1,000 classes, but from those 1,000 classes, if you want to find out only 2 classes, so you try to fine tune your network. You try to change your like your deeper layers of your deep neural network architecture. So by deeper, I mean the latter part of the network. You try to change that, and you try to fine tune it with your own requirements, and then you try to use the solution. So yeah, this is how your typical transfer learning process looks like. You try to load a pre-trained network. You try to replace the final layers of your network with fewer classes so that it runs faster. And then you try to retrain your network based on the new requirement. You try to basically fine tune your network. And finally, from the output, you try to predict, you try to check your network accuracy and improve the network if required. So this is about transfer learning, and trust me, transfer learning is very helpful and very useful. So whenever you're going for that, particularly to classification related problems in computer vision, try to search if you already have a pre-trained network on it or not. If not, then it makes sense to go for training your network from scratch. Otherwise, I would highly suggest you to go for pre-trained networks first. Now, coming to object detection. In object detection, the typical challenges which you face is, as I said, you try to classify and localize. So you do classification with localization. Basically, you try to detect and localize whether and where your particular object exists. So in such a case, the typical outputs that your algorithm should look for is Firstly, to check whether the image has a particular image, your particular object exists in the image or not. So you try to find the probability for that. So you normally call it PC. Apart from that, in object detection, you need these bounding boxes. So the bounding boxes should have a start coordinate. So in some algorithms, the start coordinate is taken as the center of the bounding box, and in some other algorithms, the bounding box coordinate is sometimes taken as the upper left corner. So it depends on what algorithms you are using, on how you are using, but you need these bounding box coordinates bx and by. And once you get the coordinates, you need the bounding box height and width as well. So you need bh and bw, and the number of classes which you have in your in what your solution wants to implement. So if you have 3 classes, it will be c1, c2 and c3. And typically an object detection problems uh, depend on this bounding box finding solution. So once you have your bounding box ready, you can easily detect your actually localize your particular object, or find the exact location of your particular object. And apart from that, an important application of this object detection is landmark detection. So in landmark detection, you have seen these Snapchat filters where you add your dog ears and nose, right? It never adds your dog nose over your eyes or forehead. It finds your exact nose location, and then on top of it, it tries to add the filter. So how does it do it? It typically does a landmark detection. So in landmark detection, you try to find multiple points or coordinates that will help you to detect the exact location of your nose, and on top of that location it tries to put the filter. So in such filters, landmark detection is very popular and important to apply. Now for object detection, there is a popular algorithm called YOLO, which stands for you only look once. So what it does is, it tries to break the entire image into an S cross S grid. Now for each grid cell, it tries to predict the bounding boxes, and from each box it tries to find out the confidence whether the particular object object exists or not. So for each box it tries to find out such a matrix. You have PC, bx, by, bh, bw, and the number of classes what you have. So this YOLO algorithm, it detects one object regardless of the number of boxes you have, and it tries to predict a conditional probability score, which means that the particular class has the likeliness of the object class which exists there or not. So in YOLO, instead of going into much detail, so once you start working with these algorithms, you will get much better like idea and information. But this is how the typical flow looks like. You divide your entire image into S cross S grid. From there you try to find your bounding boxes with the level of confidence, and finally you try to apply these concepts. So there is something called intersection over union. So if you have multiple bounding boxes, you try to take the entire this particular ratio, you try to find out the intersection over union ratio, and where it is the maximum, you consider that as the best bounding box that you should take, and accordingly you do something called non-max suppression. So in non-max suppression, if you have multiple bounding boxes, it will take the particular bounding box which has the maximum confidence score, and we try to reject the other bounding boxes. So your final detection will have only one bounding box saying that okay, this is where your exact image lies. This is how your typical YOLO algorithm looks like. And finally, your YOLO uses a sum squared error based on whatever prediction it gets, depending upon the ground truth or the base truth what you have. And the loss actually consists of 3 types of loss: the classification loss, the localization loss, and the confidence loss. And as and when your algorithm gets trained, it tries to reduce all these 3 losses and finally come up with the best bounding box with the best classification score and confidence level. Now coming to a very interesting concept of neural style transfer. In neural style transfer, you will have a content image and you will have a style image. So these style images are typically related to very popular uh, drawings done by like renowned artists. And using these style images, you try to come up with a generated image. So neural style transfer algorithms, it tries to learn typical features from different layers of your cognate architecture, and it tries to learn these for both your content image as well as style image, and then it tries to combine it, keeping the information of your content image, and tries to overlap the style of the style image. So here in neural style transfer, what do we exactly want to achieve? We want to keep the contents of your original image and adopt the style of your reference image. So through all layers of your training, the style of your style image remains consistent. So it tries to learn those uh, like the entire style parameters or the weights of those style images, and it tries to apply it over to your content image. So basically you try to define a loss function to specify what we want to achieve, and similarly you try to minimize the loss. So the main loss function actually calculates the distance between, or the difference in terms of representation between your style and content image. So for more details, I would suggest you to go through this research paper, and it proposed a neural style transfer algorithm that did not require new architecture at all, and in fact it used a pre-trained network, typically on ImageNet, and it tried to define that loss function to achieve the kind of goal with what we wanted to achieve. So the loss function, again, it will have three types of loss function, because we have a content image, so it will try to learn the main features of your content image. So it will have a content loss, and on every round of training it will try to reduce the content loss. And similarly for style image, it will have a style loss. So for every round of training it will try to reduce the style loss. And finally from the generated image, it will try to reduce your total variation loss so that it makes it as perfect as possible. So this is a very interesting concept. I tried implementing neural style transfer of my own. So from my image, I tried to apply various patterns over here, and I got these generated images. So if you like a particular pattern, you can always reach out to me and tell me which one you like the most. Maybe I can use it in some of my profile pictures if you think it's very nice and it looks good. So moving on. Yeah, now coming to the image generation section. I'm so I'll start with talking about GANs. So generative adversarial networks are very interesting networks, and the applications are also very interesting. So in GANs, it has basically two parts. It will have a generator network and it will have a discriminator network. So initially, your generator network will try to take a random vector and it will try to decode the particular random vector, and from this particular generator algorithm you will try to get a generated face. So initially, or in the first iteration, your generated face or image will look very naive, and but it tries to compare with the real images, so in such case with the real faces. These comparisons, I mean these two, are then fed into your discriminator network. So it takes your input image, both real and synthetic, and it tries to predict whether the image is a real image or a fake image. So your, for the initial case, since your generated face looks very naive and very basic, your discriminator network can easily classify and tell that it is a fake image and it is not a real image. So based on this output, it again goes through another layer of training. So your training happens both at your generator network as well as your discriminator network. So with every round of training, both your generator network and discriminator network gets smarter and smarter. So after certain rounds of iteration, there will be a particular case where the generated image will look exactly as same as your real image, and your discriminator network is not able to discriminate between those two. It will tell you that the the generated image is actually a real image and it's not a fake image. That is when your algorithm will stop and it will produce a generated image like this. So as I said initially, GANs are still not perfect. It will give you the like final outline of your images what you want to find out, but the level of accuracy we can still work on it. And there are other algorithms like DCGN, like deep convolutional generative adversarial network, that are much more accurate. So maybe you can try some of these and it might be very helpful. Now coming to variational autoencoders or VAE. So in VAE, on a very high level, typically you try to find out the probability that a particular feature or a description of the observation exists in the latent space or not. So basically, just to simplify it, from this image, if you want to find out whether the particular boy or the person is smiling or not, so from there first you try to find, so your discrete feature or value is your smile, and you try to find a probability distribution of what is the extent of it, like the person is smiling. So this is how you do a typical probability distribution. So each input image has a feature that can be described as a single or discrete values, and this is how your variational autoencoder architecture looks like. So you will have an encoder and a decoder network, and so basically what you try to do, you try to pass your input image, you try to encode your input image and try to get your discrete values, and finally you try to decode the same and get your output uh, matrix basically. So I'll try to give you this example. So in this case, you see these first four images are the actual real images. So once you pass these real images through your VAE network, it tries to first detect the latent space and the probability of that, of the particular feature, whether it here it exists or not, and then in the generated image it tries to play around with that particular feature. So basically, if someone is already smiling and if you want to extend uh, the like amount by which it's smiling, so from normal smile, if you want to make something like a mouth open laughter, you can do it using variational autoencoders. So you try to increase or decrease the probability distribution of the particular latent space of that feature. Similarly, if you want to increase the extent by which the sad face looks like, this can also be done. So this is these three, and these three are the generated images over here. So in particular cases, if you want to let's say, instead of generating a completely new image, if you just want to change a particular latent space of an image, in such a case I would go for VAs. For example, if someone is just giving a high five, and from that high five, if in for the subsequent image, if you want to change the position of that hand, maybe slightly tilted towards the left or slightly tilted towards the right, then in such a case you should go for variational autoencoder. So maybe you want to, instead of high five, if you want to make it look like a waving hand, so in such case variational autoencoders are very important. So this is one use case or one example that I have given. So from an original input image, if you want to get an image without the, let's say, the glasses of this particular person, so VAE reconstruction can have an image without the particular glasses. And similarly for all the faces, you can change just that latent space. So it won't completely generate a new image like GANs used to do, but it will try to like change the particular feature that you want to find out. It has that capability. And the same, if you want from VAEs, if you want to use GANs as well, it will give you a like GAN reconstructions also. So these image generation algorithms are very important and very fun to learn. So I would highly recommend you all to study this. Now, before concluding my session, I want to give you certain pro tips that I have found always helpful. So community participation is very important. As and when you get a chance and opportunity to pass your knowledge or even learn from the community, so always participate in such community activities. It can be events, it can be any societies where you want to work together. So as I initially mentioned before this session, that synergy is very important for learning these type of algorithms. So basically, if two different individuals having the same goal comes together with the same excitement and same motivation, it the synergy or the combined energy that generates, it helps both these two individuals to reach their goal much faster and much effectively. So I would highly advise you all to participate in community works and community forums as much as possible. Help others, and when required, take help from others as well. Now, another thing I found very helpful is Kaggle competitions. So Kaggle competitions will give you the exact practical hands-on experience. So go for as many Kaggle competitions as you can. Then I would say that in learning, deep learning or any AI related work, people often do a lot of procrastinating. So you go through a lot of study material, you go through a lot of lectures, a lot of video tutorials, but you spend very less time in working on real projects. So I would say stop procrastinating and start working on real projects. As and when you start working for a real project and for a real use case, then you try to find out, okay, for this particular project I might need to learn a new concept. Then your learning becomes much easier and it makes much more sense as well, and it becomes easier for you to implement whatever you learn in your projects. So start working on as many projects as you can and read a lot of research paper. So this deep learning, like the algorithms which we are currently working on, it is actually going through a lot of research, and people are working on a lot of new ways to come up with much more better algorithms. So these information you won't get in normal tutorials or blog posts. So better if you go through these research papers, it will give you much more better clarity and better idea of how to work with those new upcoming algorithms. So I would highly suggest that for every week you should at least read one research paper on any topic that you want related to AI, ML, or DL. And as I always say, artificial intelligence is for everyone. So AI is for all. So even if someone who doesn't have knowledge of AI, try to talk to them about AI and what AI can help them achieve and make their lives easier. So as and when you talk, then you can go about specific details and how AI can help them. So it develops the level of interest, and even they would try to spend some time in learning AI. So once we have a sustainable environment and sustainable community support, we as a entire community can reach the end goal much faster and much easier. So try learning like as much concepts as you can, and at the same time try teaching people as well. So teaching will always help you. So thanks everyone for for going through the entire session. I didn't want to go into much details intentionally because you had already a lot of sessions regarding to a lot of other concepts as well. I wanted to keep it simple. In case if you have any further queries or if you want to go into details for a particular topic, I would recommend you to connect with me offline, or you can reach me through LinkedIn, or even if you have a particular question or query, you can email it to me at this particular email ID. So thank you everyone.